Good afternoon, everyone. How are we doing? We got some questions in the chat. We got the pH question. We got question B3 from assignment 12 through 20. And we got the question on the researchers. Lily, can you expand upon that one? The researchers, I think I can find it. People are asking Mubot to give some David M. Lane in the chat. Let's hear it. I was getting my Pearson load up during the intro right there. It's a little fun on the intro. But let's see right here. If you have questions, put them in the chat. We're putting on a little music. I think we're live. It shows we're live, so we are live. We're going to hear this song. Song number 3. Best song there is. Can you clarify how to use the statistics calculator? Which one? Which one, Luke, are you thinking of? We can go into detail on that. Anything you want, we can cover here on Stat 201. I'm going to write down the questions as we're talking this over, so ask your question. We've got the pH level question. Inspiring music. We always want inspiring music right here. Statistics calculators. There's the researcher's question. Which one is that? Researcher's question. Assuming chapter 17. I'm trying to think. Like, I know a lot of them. What an action item is? Yeah, action items. So let's put here report. Project. Action items. The ones with the different colored... Are you talking about the T or the Z? Or the chi-squared? We might see some of those right here. Luke, I can go over some of those. Like, I think I might be able to like talk about those while we do it. You're probably talking about like the T. Are you talking about these, Luke? There's one in the chat. Mubot is about to drop the T. Here's all different ones. I've just dropped the T distribution. Awesome. There's the T applet. I think you're talking about these right here. And I can show some of these as we're doing it. There's the T, the Z, and the chi-squared. Mubot dropping those links in the chat. And then we've got B3. So we're writing down everything right here. Thank you, everyone, for being here. Let's throw out some points. And then we're going to take the... I've got another question. 1,000 points. Why not? Go crazy. Go big. Go crazy. Maria, thank you so much. Maria asked BS 320. Assignment 12. Assignment 12. B3. Got that written down. There we go. I'm going to add stat 201s before these. Maria, I'm putting your question third right there. And stat 201, chapter 17. I think these are all chapter 17. 2 seconds right here as I add these in. We'll get started here in 1 moment. Sad chill music. Statistics calculators, researcher question, and project. Okay, I think we got everything listed. Hey, Alyssa was using the one on the tutor homework, my stats. Let me see right here. Let me open that new window. Yeah, it has... yeah, let's do stats calculators first. I'll mention why I don't love these. Although these are like often referenced, they're not the biggest fan of these. So let's talk about the statistics calculators first. I'm not the biggest fan of these, and I'll show you why. Okay. They're fine. They work. They 100% work. But I'm going to show you why I prefer other ones. Okay. So statistics calculators. Let's have here to the main screen. Let's do it. Okay, so this is a page right here with all the different stat calculators. There's pros and cons to pretty much all of them. I don't think anyone's made the perfect stats calculator. It actually has all three we use. We don't do X bar charts here. This is process control stuff. Oh my gosh, just close that down. This is process control at the very bottom. So that's the only thing we don't do in our class of this page. We've got here the normal distribution, which is where you get your Z-scores from. So this is all Z-scores right here. Thank you, Lou, for putting that in the chat. And this is a fine resource to use. I have a preferred resource. This is the T distribution, Mr. T. Remember quantitative distributions when we're doing the distribution of the mean. And then the chi-squared is chapter 19, which we haven't gotten to yet. We only do the right-tailed test to test things more extreme than the chi-squared value we find. Now, I have a favorite applet, and I'll tell you why I like it and the one problem with it. So although I'm putting the T applet right here, you're going to see a slightly different page which has these same sort of applets right here. And I'll tell you why I like this T applet. So this T applet right here, if you look at it, is doing the same thing as this part of the screen right here. So this is the student T distribution right here. And it's got the option to do the right tail, the middle of it, the two-tailed, and the left tail. Left tail's below where you are. Now, this applet right here does the same thing. It does a left tail, does a right tail, it does the two tails, And it also does the outside tails. That's, whoops, even I'm going to get it wrong. Well, it's the outside tails. And then it does a confidence interval, I meant to say. So the confidence interval here is where we can put in things like 95% confident, and it'll show it. So I really like this applet because if you're looking at it, you can see you've made a 95% confidence interval. So I think it helps reinforce that knowledge of like, this is what a confidence interval looks like, is when you would have an estimate. The estimate's not 0, but we'd be at the center of the interval here going plus or minus, and this is the t-score we would use to create the t-interval. So this is when you're doing the confidence interval, you would use this one right here, which is analogous on this one doing the middle. If you look at how this looks visually, it is the same thing right here. It doesn't say middle, so maybe that's helpful on the other one, but visually speaking, you can see it shows the middle, and it gets the plus or minus, like that's saying the plus or minus value for the t statistic that covers the middle 95% of the curve. The other one, the right-tailed test, is the greater than test, and the left-tailed test is the less than test, and the two-tailed test is the does not equals test. So we'd enter in a t-statistic like 1.5 and get the two-tailed test, or go above it, or go below it. So you can see here the less than, the greater than, and up to 1. And that's why one of my qualms with this right here, visually speaking, is when you look at it, it doesn't change. But they are showing the same thing right here with the right-tailed test, and we are showing the right-tailed test there. And then there's the less than test, and that's the less than test right there. It just doesn't visually change as you do it. And that's why I'm not the biggest fan of it, because I prefer to see like the graphic actually change and then show the area below it to help confirm the answer. It's not just magic how it gets the number. Because if you see right here, we put in 10 degrees of freedom, 2.3 area to the left of it. So 10 degrees of freedom, t-value of 2.3, area to the left of it. What? Oh, we want to go... You have to go to this. I don't use this one as much. So you see 9.7. And a good thing about this applet is it gives a little more decimal place accuracy. So this applet can give a little more decimal place accuracy, but if I really, really want that decimal place accuracy, there's one last place I go. Of course, Brian's going to go to coding to get his real decimal place accuracy. And we'd go to is it PT right here? And we put in, 2.3, 10? And there's the exact, and we can even go crazier. So I think the applets are good to kind of get you a baseline of what you should see. And is that not digits? Oh, it's options. Oh, I just lost it all. So if you really want to see what's going on, you could do this right here. Homework on cinco? Sorry. Lo siento. Cinco de mayo. Homework assignment aquí. Yep, cool. We got an assignment. Does that make sense, Luke, to your question? To me, if we want to go super duper detailed, I would go to a calculator like this, which is going to get the very fine decimal precision on it as far as you can see. So even here with it reporting 4 decimals, that's good. Please tell me if you think like the applets didn't give you a good enough answer. But this right here gives an extra decimal where this one doesn't. I wish they had an additional decimal. That's my only problem with this one. But I really like this because it has the normal curve if you want it, the chi-squared if you want it. So you've got, and we don't use the F in our class, but you've got all the applets right here on statdistributions.com. So I'm a big fan of this one because you basically can go to the normal if you want, the student t if you want, the chi-squared, and we don't use the f, which is the ratio of 2 chi-squareds. This one's good too, but it doesn't actively change. It just does the same things, like this is the normal curve right here. So it's the same thing as being on this page and putting in the normal curve. Also, you can't change the mean of this distribution. So this works for homework assignments where it says things like you change the mean and the standard deviation. So you can actually change it like the David M. Lane. Researcher question? Yeah, and which one is that, Lily? Can you expand further? I've got that marked. Expand a little bit further. The researcher questions. What else? Is it the water? Is it the 2 glasses one? Is it like they're doing I think it's the cup size one. They're doing a small and large cup, right? I think that's the one. I think it's the researchers looking at small and large cups. I think that's it. Off the top of my head, I think that's the one you're talking about. We'll take a look and get working on it. Can we do the fat content of beef and hot dog? Yeah, of course. Yeah. Good to see you here. Let's head back to the main screen. We got some questions listed down. Let's see here. We're going to put researcher question. We're going to do pH, then researcher question. It does. I think the researchers they're investigating large and small cups of water. I think. So Lily, correct me if I'm wrong right there. And beef and fat. Oh, thank you. I haven't played this one lately, so I play it more often. People notice it. People notice, hey, this new song's pretty chill. I got a bunch of songs. There's so many songs we haven't played that some of them aren't chill. Some of them are more hype. We don't need hype every day, though. Hackerman song is hype. We're doing pH question, then we're doing researcher question, which I think is the cup size question. I think the researcher is cup size. Okay. We got the pH question ready to go. But do you finish up my answer question? You're welcome. Yeah, anytime. Good job, Luke. Oh, thank you there, Cerael. I missed the rock music. Oh, we need to bring back the rock. Yeah, he's still gone. I'll try to reset before class. I need to reset the computer. I didn't save my profile on the thing I used, so the rock still exists. Oh, wait. Okay, I'm gonna do something. Okay, give me a second, and then we're gonna do this problem. Called a bad idea. Okay, I shouldn't do it. It's not letting me change profiles. Maybe it's... Oh, I just did something. Yeah, you can tell. 2 seconds, and then we're going to get serious.
It doesn't matter!
Rock's back. Fixed it. We fixed it. There we go. Rock's back. What is the margin of error for this confidence interval? It'll be half the length of the interval. Thank you, Madison, right there. We got the rock back. Thank you, Zachary, right there, saying you missed the rock. I was like, I can fix that. I can figure out how to... Sorry, I did a little technical stuff right there. I was working on the technical stuff, and we've got the next question ready to go, but this is all the... That's all the fun in the background. I was working on that. So I was like, I'll fix it. I'll figure this out. Okay, now that we got that fixed up, we're going to do some more. Madison, good question right there. Let me take the timestamp. Sorry about that. Little fix in this touch one. Here we go over to the main screen. Let's do it. Okay, so we have a researcher is testing the pH levels of water. Now, what they're doing over here is actually they have 3 groups. But why is it called the 2 sample T? Who can tell us theoretically which Rock knows that one of those groups...
It doesn't matter!
One of those groups doesn't matter because they're only going to test the L and the M. So why is it called the 2 sample T? Why do we call it it is a categorical quantitative variable. That is correct. Categorical quantitative, and they're not going to look at this. They're just trying to mess with you basically by giving you more stuff. But why is it called the 2 sample T? Think why it's called 2 samples and then T. Well, T relates to a quantitative Y. So the T portion means the Y variable we're analyzing is quantitative. Does that make sense? So when you do a T test, the Y variable is quantitative, but it's called the 2 sample T. Why? Why do you think it's called the 2 sample T? Because we're comparing, just go with it, who knows, for 100 points, why is it called 2 sample? And then we're comparing quantitative measures. It's kind of redundant. It's called 2 sample because there are, let's take a look right. Because there are, why is it called 2 sample? Why do we say 2 sample T? There's 2 means being compared. There's 2 samples. We take a sample from the L, we take a sample from the M. So we're comparing these 2 samples to each other. Does that make sense? You have 2 samples and you're comparing them and you're analyzing the difference between the means right here. Those are medians, I know, with the box plots, but the means might be somewhere in here. The means might be there. So we're comparing, and I know you're given a 3rd group here, but as Rock always says,
It doesn't matter!
they're not using that 3rd group inside of this example. They're only comparing the L and the M. Now, there's a great way to figure out this question right here because we know the null always has the what? Yeah, we can do that one. I think that's the researcher question that Lily's referring to. This is a researcher's one also, but I think the null always has the equal sign. Great job. So that literally narrows down the answer to right here where the null has the equal sign because you say mu the first minus mu of the second, which is the difference between the means. That reads the difference between the two means is equal to 0. This reads the difference between the two means is not equal to 0. So that's what they were testing. This question is pretty interesting because it goes over the conditions next. Do I still have that? Should have saved those notes. Condition 1 is that the data is randomly selected. Condition 1 is random, which they're calling the independence assumption, which can lead to randomness. I don't love that they do that. We say random. Condition 2 is what? If you've been practicing with us all semester, you know condition 1 is random. Condition 2, I have to do it. Condition 2 is what? Which they don't mention, but we should know. Condition 1, random. Condition 2, and then we have to know condition 2, which is less than 10%. Yep. I think you just hit a button right there. Less than 10%. Great job right there, Zachary. So they need to take less than 10% of all the water or whatever they're taking to test. I think they probably did that. They don't mention it here, but it would need to be less than 10% of all the population was sampled. They're probably good on that. The third condition is going to be what? Hey, Priya, great to see you here. Is the third condition success, failure, or nearly normal? Mebot saying hey to everyone in the chat. Is the third condition success, failure, or nearly normal? And why do you know that? So a lot of people say, well, it's success, failure. And you say, what? Yep, I think we're doing that one next, Lily. You got it. It's nearly normal. Great job, Austin, right there. And why? We'll make Austin a mod right here. Why is it nearly normal, Austin? You are correct. How did you decide it's nearly normal? A lot of people say success, failure. And I'm like, slow down. We need to ask, because it's quantitative, right? Zach points out there we're dealing with a quantitative Y variable. It's a t-test. Mr. T is mean. I'm sure he's a nice guy. So since we're doing a mean, we're doing quantitative. So thus, it is nearly normal. So we have to ask, are these nearly normal? Are they? Maybe. I don't know. They're asking which assumptions we have to check. Now, the last condition, because we have two means, we have to assume that the two means are what of each other. Now, funny enough, I was actually doing one of the other versions of this last night. Haslam Friday, of course. Be seeing you in class here. Adam, keep asking those questions. We got it. We're doing some shiny today. We have to ask, are these two means what of each other? Which means they don't impact each other. An assumption, when we test two means right now, is that mean 1 is what of mean 2, which means, like, let's say you have a friend and they're seeing how fast they can run a mile. And then you go out without a knowledge of what they're doing and try to run a mile also. Your times would not depend on your friend's times. Like, you want to see who's faster on average. So you run miles at different paces, they run miles at different paces, then you compare times and look to see if there's a difference between your times. That's independent right there. Now, if you were to run miles and then train and rerun miles, your times after training would depend on your times before training. Does that make sense? Like a before and after sense, which this doesn't cover. But the idea of a dependent mean is when we say something like you go on a diet. So you start off like 250 pounds, and then weeks later, you end up at like 180. And your weight after would depend on your weight before. So those would be dependent. Yeah, do some driving route. You got it, Luke. So this passes the independent groups, and that's when you have two means. So write that down on a note card. When we have two means, we need to check the two means are independent, and I call that condition 4 after random, 10%, nearly normal because it's quantitative, and then two means for the fourth condition. Now, the last thing right here wants to know what we do with the null hypothesis. Anytime you see the decision on the null, we should look towards the what? What do we look at on the decision for the null? With the decision on the null, I should look right to the where. If you're asking what I should do with the null, that is decided based on the what. So good practice right here. If you know it's asking what I do with the null, how would I decide that? And yours might be different. Watch out, this question changes. How would you decide what to do with the null hypothesis? How will I know the answer to this question? When we look at the decision on the null hypothesis, we need to go to the p-value. Great job right there, Zachary. So when the p-value is low, what do we do? Great job, Priya, right there. When the p-value is low, what do we do? When the p-value is low, which this p-value is low, what do we do? Not trying to trick you. It just did that on its own. When the p-value is low, we reject the null. And then you're saying, I no longer believe the null. If you no longer believe the null, well, the alpha is the point at which you reject. Does it say alpha in here somewhere? Alpha is the point at which you reject. Alpha is a bar saying, I will reject p-values below this bar. Usually set to 0.05. So I don't see it in here, but we would assume otherwise alpha is set to 0.05. So alpha is just a bar. Our p-value is below alpha. When the p-value is below alpha, usually set to 0.05, we reject the null. So does that make sense right here? We're rejecting, and thus we have evidence for the alternative because we no longer believe the null. There is evidence. So reject, there is evidence. Do not reject, there is not evidence. Or fail to reject, there is not evidence. Does that make sense right here? It's a good question, especially at the end right here, practicing and knowing how to read the output and what it tells you, that there's evidence of a difference between the two means. And so it assumes the alpha is 0.05. Unless otherwise stated, always assume alpha 0.05. It's good stuff right here. And interesting enough, you enter in this T statistic. Great job, Priya, right there. We'll do this, and then we'll do the next question. If you go to the T statistic, which is 16 point something, does it tell the degrees of freedom? Degrees of freedom, 125. And T statistic, 16.3. And the two-tailed test, the p-value is basically 0. You're way off the curve, telling you that this result is super unlikely given the null is true. So the difference you observe between the two groups is super unlikely. Great job right there, Alea. You're seeing it. It's like, okay, the p-value is basically 0, telling us that what we observed as a difference between the two means is super unlikely given there is no difference. So we reject that there is no difference. We have evidence there is a difference. Good practice for the test and for the project and knowing how to read this, that I reject that there is no difference between the means. I have strong evidence that there is a difference between the means because what I observed in my sample results was super unlikely. I guess we close the other one out by random chance. The p-value of basically 0. Well, that's got it. We're going to do the researcher's small and large glass question coming up here next. Wrong button. I always click that wrong button. I got to make my things more intuitive. Already got the question, getting the timestamp ready to go. This question, then we're going to do through 20, and then we've got, someone mentioned another one, driving route. Chapter 17, driving route, bike driving route. So, what do you think? Leo knows the answer to this. What do you think a lot of these questions will come down to? A lot of these questions will come down to our ability to identify what. Very important as we read problems. Let's go check it out. Who's got it in the chat? It's time to wake up because what do you think a lot of these, Caroline, great to see you here. It'll come down to
notation, brother.
Thank you, Leo, for inspiring us right there to do some notation. Now, what's really great about this problem is it gives you all the notation for the most part. For the most part, you can see that we have the notation laid out for us right here. Now, why do you think, just once again, we'll repeat this endlessly till it's just ingrained in our heads. Why do you think we are doing a 2-sample T test? I want us to look at this notation, and I want you to think, why are we doing a 2-sample T test? Why are we doing? It's important to know why. Why are we doing a 2-sample T test? Because T implies we're comparing what's, and we have what's. T implies we're comparing two means, right? So 2-sample T means we have 2 samples, and there's 2 sample means, and T's are mean. Does that make sense? So the more you just say it, the more you practice, oh, the 2-sample T test compares 2 means. We do have tools and techniques questions, so you just have to know when to use it. So we're comparing those 2 means. And we want to look at the what's between these 2 means. We're going to look at the what's between these 2 means right now. With either the 2-sample T interval or the 2-sample T test, our main goal right here will be, and maybe it would look better if I did it this way, because it's going to look like what we're about to do. We're going to look at the what between those 2 means. We're going to look at the what between those 2 means. The main goal of a 2-sample T test or 2-sample T interval is to compare and understand, starts with a D, looks like that symbol right there, the difference between the 2 means. Like, how far are they apart? Is there really a difference? Is the difference equal to 0? And that's what this question is starting off with. They give people a large and small glass, and they're asking, do people pour a different amount into these glasses? So in the large glass, they're pouring 6.88 ounces on average, and the small glass, they pour 5.22. Just imagine you're given a glass, and we say, pour some soda in it, and you're like, oh, thank you. 5 ounces of soda is not that much. You're like, oh, let's take a little bit of soda. But the larger glass, they pour more, but there's a larger standard deviation, more variation. Like some people pour this, some people pour this. The smaller glass, there's a little less poured with less variation in it. Variation would be like the just inherent differences between what people pour in the small glasses, the 26 observations that we have of people pouring into the small glass. So the mean for the smaller glass, and this is the null hypothesis, the null always has the what? Mu1 minus mu2, where I think they're using small glasses mu1. Yep. What do we always say about the difference right here? The null is that the difference is equal to 0. It's going to help right here is the same. So it's the same, that there is no difference. You could just mathematically bring this to the other side, just so you can see that visually. It helps people sometimes to realize the algebra right here makes sense, that all you're doing is you could just say mu1. I know it's like, why don't we just say that? You can, but it doesn't do the same format. So it's just saying the first mean is equal to the second mean, the truth for them, not in the sample. The sample is just what we observe. We're talking about the truth, that there really is no difference. So then it says, where is it? Did change? Here it is. Did the glass size change the portion people took? So we're asking, are we asking is one greater? Is one less? Or are we saying, is it different? What does it sound to you like we're asking? Are we saying, do people take more for the large glass, less for the large glass? Or is there a difference when people take different glasses? What does it sound like we're asking? Because it says, does the glass size, we're asking, is it different, right? Does the glass size change how much people take? So they're not giving a directionality on this. They're just asking in general, is there a difference? And for that, we would go right here, and is it different from? Are there differences between how much people pour in the glasses? So we are going to use the what symbol right here. What symbol are we going to use? Because we're asking, is there a difference? So they're asking, does it change? Is there like people take more or less with this one? We're not asking for a particular way it goes, but which one should we use now? Because we're asking, is there a difference? The does not equals. Great job, Zach. Zach, we're throwing you some 500 points. Excellent work today, Zach. Doing some great practice right here, answering all the questions. Keep it up. So we're asking, is there a difference? Now, this is where the question jumps to finding the t-statistic. When we find the t-statistic right here, we have to know the equation. It is considering this to be mu1 and all this, the second group right here. So let's take a look. Y bar 1 minus y bar 2 over S1. You do get these formulas on the test. S1 squared plus N1 plus S2 squared over N2. Okay. And so the difference, 5.22 minus 6. What are we doing? We're taking the difference and whatting it. We're taking the difference up top right here and whatting it. Like, what's the whole point of this procedure to get a t-statistic? The whole point of this is to take the difference and what it. Like, why do we do this? We want to look at that difference and what it. Like, we have to give it context. We have to know, is that really a difference? So we're whatting the difference with this procedure right here. Make sure to write all. We're standardizing it. Ashton, great job right there. We're dividing by the standard error, which gives it context, right? We're standardizing this difference, which is what we do for every test. We take a difference and we standardize it. So we're asking, is that really a big difference? Well, let's give it context. How many standard errors is this distance? So that's just literally taking this right here and putting it in units of standard errors to tell us, is it a lot of standard errors or a little bit of standard errors? The bigger the amount of standard errors it is, the less likely it is to occur by random chance. So the top part of it is the difference, as you can see, y bar 1 minus y bar 2. And the bottom is the formula for the standard error of the difference between the two means. So that is how we run all tests, whether it be y bar minus mu naught over s over square root of n. Same thing right there, just scribbling it out. That's a one sample mean test, which is a different standardized. So now let's go here and do the t-statistic. It has degrees of freedom, which we're going to have to find. Is there time we can do that? Yeah, I think we're doing that one too. I'll put that on here, Priya. You got it. I think we have just enough time. We got a good lineup of questions. We got 1 hour left. And so what we need to do is we just need to solve this equation. If anyone wants to solve this with me, that's much appreciated because I do make errors every once in a while. So I'm going to solve the standard error on the bottom. There we go. There's that. That looks right-ish. That's the standard error. Make sure to follow your mathematics. Check it carefully. It's already been square rooted. Okay. I did it reverse. There we go. Oh, and so Priya, let's check this. Let me copy my answer in the chat, Priya. I think we got the you bet, Cerael. We got it. I copied my answer to the chat. I'm gonna double check my work. Priya, double check your work. People are getting Zach and Priya confirmed Brian got a wrong answer. Ooh, what did I do? I was just making sure people were doing that. I squared that, right? Are you guys square rooting the bottom of that? I think I'm about to get the same answer. Can we get, let's get confirmation. We're getting different answers, and that worries me. Might have to check it in. Oh, you might think that that's a 16. That's a 26. Did you guys use 16? Did my bad handwriting trick you right here? That might be where the issue was. That would create a smaller standard error. My bad handwriting might have convinced you that that's a 16. I thought it said 76. Oh, 76. I thought so. Okay. There we go. I was like, yeah, it's my bad handwriting. That's one for Brian right there. Yeah, I thought something was. I was like, something. It has to be a communication issue, because we're getting different answers, and I'm worked it a few times. That's where the 1,000 points. Brian can't write. We all know that. Now we're confirming the same answer. Okay, so we've got the answer right there. Make sure you can read your own handwriting. Don't be like Brian. I bad handwriting. There's the T statistic. Ah! I copied everything, Zach. Okay. Okay, now we need to go find the p-value. This is actually the tough part of the problem, because what is our trick for remembering how we remember the formula for the degrees of freedom for this test? How do we remember this formula? And I want you to remember, so if you're new to this, how do we memorize the whole formula for this? Oops, where is it? How do we memorize the whole formula? Who knows our trick for memorizing the whole formula? It's too complicated, right? That's all you need to know. Oh, 3 decimal places, thank you so much. It's too complicated. The 2 sample t degrees of freedom is too complicated. So where do we go for this? We go over here. So we need to enter in the information from the problem, which I think we deleted it. So here it is down here. I'm going to put it over on the side and I'll show it. I'm going to write it in and then I'll show you it again. 26, not 76. Make sure you can read it. And then standard deviation 1.87 and 2.84. It's probably like 45 or something. 50. Here it is right here. You have to go to the applet. We don't expect you to do this during the test. Sample size 1, 26. Sample size 2, 30. Standard deviation 1, 1.87. Standard deviation 2, 2.84. So now where do I need to go? Someone help me out. Where do I go with this degrees of freedom, which tells me which t I am using? This tells me the shape of the t. So where do I go with this t I just found to go find the p-value? So now I need to take this t I just found and go where with it? T-applet, great job, Cerael, right there. I need to go to the t-applet. Someone, great job, Priya, another 100 points right there. We're going to go over to the t-applet and enter in, and we're going to take our number with 3 decimals, or why not all of them, and we're going to drop it in. Now, I believe we're doing the 2 sample t. Really? Whoa. Something's weird in the neighborhood. You know what I'm actually going to do? It doesn't let you enter in that last decimal. I'm going to enter in this. Now, the reason I can do this, so this is a little bit confusing, so I'm a little mad at my applet today. The reason I can do this is because I'm doing the 2 sample t-test. And so how does this applet work when I do the 2 sample t-test? The 2 sample t-test, and we can see if it would give the same answer. Ooh. The 2 sample t-test does what? It shades on both sides of the curve. So in terms of this being positive or negative, say it with me. It doesn't matter. Does that make sense how the 2 sample t-test works? So I'm actually, if you notice, it doesn't matter which way I do it. So I'm actually entering in the extra decimal. Do remember we do have the negative on it. So it is a negative t-score because of the way we subtracted the difference right here. We did get a negative value. Because 5.22 minus 6.88 is negative, so the t-score is negative. But when you do the 2 sample or the 2-sided test, whether it's positive or negative, it just reflects it on either side. So that's important to kind of understand conceptually. So I'm able to get that extra decimal place accuracy with a p-value of 0.035. So the p-value right here round to 4 decimals. Now that scares me a little bit. I think it will accept this. I'm a little bit scared on this one. So actually what we're going to do is we're going to use and confirm via the applet that Luke was putting in the chat that Alyssa had. If you were to get something wrong here on this one, let's see if we get it right or wrong, and we'll see Alyssa's applets right here. Thank you, Alyssa. We got here the 2 sample, degrees of freedom. It's just sometimes these questions can be a little cranky. Degrees of freedom, this. And where's our T statistics over here still? And we're doing the 2-tail, and the p-value is, whoa, what's going on here? 0.0188. What have we done? That's not right. Look at this. We can't copy numbers. We are doing bad at copying numbers. Brian needs some more coffee. There we go. So that's 0.0118, and Brian's learning how to copy numbers correctly. My applet says this, and the other applet says this. They're virtually identical. The other one gives extra accuracy. If we get it wrong, it's going to be that, and please let me know if you get this one wrong, but you have to make sure you're using the T applets. A lot of people accidentally use Z applets for this. You can't use this. You don't use the normal curve. Normal curve is going to get you way further off answers, so don't use the normal. Either way, Rock knows once again. It doesn't matter. Because what are we going to do with the null hypothesis here? Even if we enter it in as the more decimal place accurate or our current number, what would we do with the null? So who's got me on the null hypothesis at the alpha level of 0.05? So how do we know reject or fail to reject the null? Let's talk over that. We're going to reject. The p-value is lower than alpha, either which way. So the p-value here is lower than alpha. We reject the null at the 0.05 alpha level. I reject the null. The data has sufficient evidence, provides sufficient evidence that there is a difference. Now be careful, they were testing to see if there is a difference via the null hypothesis. Are we going to miss that one little problem? Oh, we did. Ooh, please let me know. Really? Oh, whoa. What's... Someone said it earlier. No.
I am Mubot.
Someone said it earlier. Where's the error? Someone said it. They said it. Who said it? It was Ashton said it. Ashton, I'm sorry. You tried to warn me. I didn't listen, Ashton. This is definitely an email Brian one. We have lost our streak. We were on like a 2-week straight win streak on this. Ashton, that's it right there. That was the thing. Ashton said, I warned you. You didn't listen to me, Brian. Ashton, that's worth 1,000 points. Ashton, thank you for warning us. We should have heeded the warning. You were right. On the question about standardized testing, if our margin of error is small, what would everything decrease? Correct. If the margin of error gets smaller, the test statistic got smaller. Might be what you're going towards right there. If the margin of error got smaller, the test statistic the interval was built on got smaller. Make sure to put in your decimal place accuracy. You will lose points. Once again, please do email me if you get this wrong due to decimals. But however, if your number was something like this right here, that would not be close enough. Because the T and the Z will come to different conclusions. And if you were to use the Z statistic, here we'll go to the applets I love. If you were to use the Z and do a 2-tailed test, you would get that p-value right there, which would be wrong. So if you're kind of close, it could be because you use Z's. So watch out. These are sometimes ones where someone says, I was off by just a couple hundredths, but that might be because you use the Z instead of the T. But if you're off by like the 10,000s, then it's like, oh, my Pearson's just being mean. But please let me know, and I evaluate each thing on a case-by-case basis. It's just sometimes people accidentally use the Z instead of the T, which will come to different conclusions sometimes. Like reject or fail to reject. We've got more questions right here. We lost the streak, but don't worry. We got more questions. We're going to do a little 320, come back to 201. Stay tuned. Okay, we've got after 320 right here, the beef and fat hot dogs, the project action item, the bike driving routes, and then I saw another one we need to add right here. Fat content. We got the fat content. And store A, store B shopping. Okay. We will get this. You lose a streak, you start right over. That's what you do. When you fall, you get back up. Don't give up. Just shake it off. Shake it off. We're gonna get copyright struck. Where is assignment 12? Oh wait, it's modeling something. It's got a different name to it. Model building. check this out right here. Streak starting back up right here. You got it there, Luke. You know what's up. Zachary. See, wait. Perfect. Corrected it. We're good. Just correct everything you're saying and you'll be good. Okay. So we got the model building. The question was B3. Okay. 4140. Here we go. Okay, so this is 320. You're going to get to see some cool stuff right here with model building. And B3 is the following. In the model with the lowest AIC, you see that the day of the week is in the model, but is only represented by indicator variables. Day Sunday. No other indicator variables for blah, blah, blah. And if you're wondering what this is like LaTeX writing to make cool things appear. So you can actually, if you don't know how to code, which sometimes I don't know how to do the LaTeX coding, you can go down here. Really, it looks like that. Or that's weird. What is the implication? Other words, which days of the week are being treated together and which are being treated separately? Cool. So did you see that the day of the week in the model, but is only represented by the indicator day Sunday? Cool. So this goes to a theoretical question of how do indicators and reference levels work. So I think it was, Maria, are you still here? So you're going to get to learn something about, so if you're in 201, you get to learn something here about 320. Who knows the days of the week? Like, can you start me off with what is the first day of the week? Maria, awesome. Just start me off on the first day of the week. Preferably, I don't like how we do it in English. Preferably, and in honor of Cinco de Mayo, the first day of the week is Monday. Because if we say something's the weekend, now I know we say it's Sunday. I'm saying what I say. Good to see you here, Andrew. I think the first day of the week is Monday, even though Sunday is the start of the week. Why do we call it the weekend? It should be called the week joiner. We should say, oh, we're in the week joiner right now, not the weekend. The weekend should be Friday, Saturday if Sunday starts the next week. Oh, it's the weekend, Friday, Saturday. Sunday would be the start of the next week. We got to be accurate here. So what we have right here are the days of the week. Now be careful. 320 will know this quite well. But what day of the week is the reference level? So we've got all the different days of the week. What day of the week is the reference level? This is a good review for 320. What day of the week? Good to see you here. What day of the week is the reference level? And it'll be points, exclamation mark points. Not Monday. Monday's the start of the days of the week. But what is the reference level? The reference level is what everything is compared to. Not Sunday. Friday. And why Friday? Why is Friday the reference level? Why is Friday, and it's rather arbitrary, but why is Friday the reference level? Why is Friday the reference level? First alphabetical, yep. So think about this, and one of my favorite examples to talk about this is using my family. If I were to tell you, here's Brian, and then here's Darren, and here's Emily. Emily is -3 years. Darren is +2. Brian is 0. These are the ages of the people in my family. So you can tell my brother is 42. So how old is Brian? How old is Brian? Darren is 42. Totally telling him. Emily's 37. How old is Brian? Brian is how old? You can figure that out from the math right there. Darren's 42. Emily's 37. Brian's how old? 40. So, with that in mind, when you think about this, these values are using Brian's age as a what? These values are using Brian's age as a what? These values are using Brian's age of 40 as a what? Oh, you got this. Good to hear that. Congrats, Andrew. Those values right there of +2, -3 are using Brian's age as a what? As a reference. Now, why is Brian the reference for his family? Why is Brian the reference for his family when it comes to talking about ages? Brian should be the reference, not because he's the middle child, but Brian's the reference because when it comes to names, Brian's what? first alphabetically. And that's just how reference levels are decided. But what if we were to take, this is weird. Now, Darren still exists. I don't like talking about my family members not existing. What it's saying, no. What happens if we have this occur? Oh. Do the other days of the week still exist in the world? Do the other days of the weeks still exist? We can. There's ways to reassign. It's called relevel. The function is relevel. We don't usually do it by default. Do the other days of the week still exist? So there's Sunday now. And and this goes to model hierarchy, we talked about last class, where do things go that disappear? Things that disappear go into the where, like all those other days of the week. Where do they go? Where do those other days go? All the days of the week we delete. We've ruined the model hierarchy now because we don't have indicators for the non-reference levels days, but they have to exist somewhere. And here's a hint. These are the days that are Sunday. That's Sunday right there. So where do the other days go? Where do the other days go? If we delete things as indicators, they go to the where. If we don't have indicators for them, they have to still exist. We have to make predictions for them. So they go to the where. Hint, they're not Sunday. So if they're not with Sunday, they'd have to be where? There's only one other spot for them to go, right? So if they're not the level Sunday, they've gone to the what? If they're not the level Sunday, they've gone to the what? Where would they go? They're not with Sunday, so where have they gone? It's only one other spot. Where would they go? So we have days that are Sunday, because we're going to say, if it's Sunday, this is how we make predictions. They go to Friday. So when we delete indicators, they go to where? If an indicator is removed, that level goes to the where. So finish sentence. When an indicator is removed, it becomes part of the this. If an indicator is removed, it becomes part of the this. Like in terms of general sense. So like when you don't have an indicator, you've destroyed the model hierarchy. The indicator would then become part of the what? Because you have to make predictions for it. So part of Friday in this example, but in the general sense, it would become part of the what, which Friday is the this for this example. But whenever an indicator is removed, it always goes to the what, because you have to make predictions for it still somehow. So it becomes part of the equation and the way we form the this line or this level. Well, it's in X, but what is Friday? Friday is the what for this. So whenever an indicator is removed, it then becomes part of the this level, which Friday is for this example. You're right, Abigail, good work, 100 points, keep it up. So you're really close. You're like, whenever an indicator is removed, it has to still make predictions. So those X's, those levels, which we don't have indicators for anymore, become part of the what level, which the other days have now gone to Friday. Friday is the what level. It's the one everything is compared to. It's the one that's first alphabetical. They become part of the... I've been on top chat this whole time. Part of the reference. Great job, Abigail, right there. So think about this. How could you describe the days now? If you wanted to describe the day, there's Sunday, and then there's what? I mean, we kind of make it a little clear with this right here. There's Sunday, and then there's what? Like, good to see you here, Caroline. There's Sunday, and then there's what? Like, you have a day, which you have a variable which tells if it's Sunday, and then everything else would be what? Like, you make predictions special for Sunday, and then you have another line. You have two lines, a Sunday line and a what line. Think about complements. This goes to stat 1. There's like a predictions for Sunday, and then there's predictions for what? And what are the reference days? The reference days just it's either Sunday or it's what? Like, it'd be like, today is Sunday or it's... And that's every other day. So think about how we could talk to someone who doesn't know about the reference. Be like, oh, this model makes special predictions for Sunday, and then it has predictions for every other day, which is not Sunday. So you could re-describe this as the model is doing pretty much Sunday or not Sunday. Does that make sense? Like, there is the reference line, which is not Sunday because it's all the other days. Does that make sense? Don't worry about the alphabetical order anymore. We're just talking kind of theoretically that there is a not Sunday line because that's every other day is with Friday now. The reference line is Friday, but Friday also has the other indicator variables with it. So it's no longer just Friday. It was created from Friday, but then all the other indicators went into it. And so now there is the kind of not Sunday line. It was created from the Friday line. So it's important to know that's how it was decided on what things went to. Does that make sense right here, Abigail, that we had a Friday line, we removed out all the other indicators, so now we could describe the Friday line as the not Sunday line because there's only two lines. So there's either it's Sunday or it's not Sunday. Does that make sense theoretically? Awesome. And that's what happens to indicators when they are removed. They go to the reference level, and the reference level Friday is now better described as a not Sunday line. Yeah, well, this is it right here, Parker. This was B3. We worked on it yesterday too, and the day before. We got those videos marked. So we've done a good 50%. What is the implication? So what does this mean? In other words, which days are being treated together and separately? How would we answer this? So which days are being treated together and separately? So so what does this mean? What does this mean? What does this mean? We've broken the model hierarchy. How does that mean our model will make predictions? It'll have two lines, right? And then it's gonna make predictions on blank or blank, right? Well, that's how the model. Well, it's not that we're making like different models on it. It means like we either make predictions based on it being Sunday or make predictions on it being not Sunday. And there's only really two days for us. There's the Sunday day and the not Sunday day. Even though there's 7 days of the week, we're only acknowledging two different ways to make predictions right here. That we have Sunday and we have not Sunday, which was the Friday reference level. Does that make sense, Abigail? Like everything is joining into the Friday reference level. So if it's Tuesday, the prediction would be made the same as choose another day. If it's Tuesday, we'd get the same sort of prediction as it's what? If it's Tuesday, you'd get the same sort of predictions like if it was what? If it's Tuesday, like our model's making predictions and it's Tuesday, you'd get the same sort of predictions if it was what? Like it wouldn't matter if it was, well, exactly any day that's not Sunday. Or, well, no. But if it's Friday, Tuesday and Friday will give the same predictions. Tuesday and Wednesday will give the same predictions. Tuesday and Saturday will give the same predictions. Wednesday and Saturday will give the same predictions. Thursday and Saturday will give the same predictions because all those days I'm talking about are what? So once again, and so fill in this blank right here, all those days will give the same prediction because they are all days that are this, like Tuesday, Thursday, Monday, Wednesday, all those days. If we're predicting on a Monday versus a Wednesday versus the Thursday versus a Friday versus a Saturday versus a Tuesday versus a Wednesday, all those days are days that are what? Hence, we get the same sort of prediction because we have two lines right here created, and all those days I've described are what? I left out one specific day because every day I'm talking about there is not Sunday. So we have predictions for days that are not Sunday. And then we have predictions for day like Sunday, when it is Sunday. That gets a special like, okay, if it's Sunday, we predict differently. And that's what's happening right here because Friday was the original. Like if you go way back in time, a model created this way would make predictions differently for every day. Does that make sense? A model with these 6 indicators is going to have predictions different for Saturday, Sunday. Every single day is going to get different predictions. But what we're looking at right here now is our model only has Friday and Sunday. So every other day is in Friday, which is the other days, and they go into Friday. So we could just recall Friday, like say it's the not Sunday level. So there's like Friday, which is the reference, but Friday has all the other indicators inside of it now. So because they went away and they become part of the reference. Does that make sense? There's a lot of theory here on model hierarchy and what happens when indicators go away. So Friday has the other indicators inside of it, and it is now called, better attributed to be called the not Sunday line. Good stuff right here, and good theory on what happens with model hierarchy and indicator variables, on what we remove out with levels. Let me know if you have more questions. We're going to do a little more 201. Back to the main screen here. Good practice. It comes down to knowing the theory. A lot of theory, a lot of practice. That's what we do right here. We teach the theory. Let's see. Next question is beef and fat hot dogs. And we got action items coming up here next. Maybe I'll drink a third cup of coffee today. Maybe that's a bad idea. Beef and fat hot dogs. Let's go grab that question. Should Brian drink a third cup of coffee? If people say yes, I might do it. And that's a bad idea. Got beef versus fat hot dogs. There we go. Timestamp. Let's go to the main screen. Okay, so, ooh, this is a really good interval. Listen into this question because we got probably the most fascinating interval we could get that's pretty easy to understand. They're testing the difference between meat and beef hot dogs. And so imagine you go out to the grocery store and you buy, doesn't say, but let's say like a 6-pack of each. Now you're going to measure the fat content between each. Now you have to look at your interval and understand what the interval means. If, hypothetically, in your sample, you saw something like the average of the beef hot dogs was 18 and the average of the meat hot dogs was 10, what is your best guess of the difference in grams of fat? Let's put G here for grams. What is your best guess of the difference? So you're saying you sampled the hot dogs, you got the meat hot dogs, you got the beef hot dogs, you sampled them, you saw that 8, right, Cerael? Does that make sense? Like you sampled these and this is the average. The means of these, the mean of the first in your sample minus the mean of the second in your sample. That's how the math is done. We're saying we saw a difference of 8 in the sample. Like, so what would you say to me? If this is beef and this is meat, you'd say to me, I saw on average the beef hot dogs had what? Just like had what? Like just think about how you're communicating this. You're testing how much fat is in them. You're doing some sort of like chemical test or however you do it. I don't know, they like burn it or whatever, but you're seeing how much fat is in them. And you're saying, oh, I saw in my sample what? I saw in my sample. What did you see in your sample? I saw that the beef had 8 more grams of fat than the meat. Does that make sense? Just with the numbers. We're just making up numbers to kind of think through what they're doing in this problem. And so does that mean for certain that there's 8 more grams? Like we would say, oh, I know for certain. Well, what would we need to make to estimate the true difference? Like in reality, we'd need to make a confidence interval. And this y bar 1 minus y bar 2, which you calculated up there, would be at the very center of the interval right here. So you'd say my best guess is 8, but then every single interval needs a what? Every interval would need a margin of error. So the margin of error on this interval is what? See if you can calculate the margin of error Brian has created on this interval, which is kind of a lot of this question right here. So what do you think the margin of error is of this interval? Who can calculate? Just do it real quick, see if you can get it. Boom, know how to get the margin of error. Good practice. What is the margin of error of that interval? Because we saw a difference of 8. We think it's somewhere between 5 to 11 grams of fat difference. Cerael, great work right there because it's half the length of the interval. Plus 3 minus 3. The interval length is 6. You can divide that in half and get right there half the length of the interval. Good practice. Margin of error is half the length of the interval, which this question goes to later on. Now, what's interesting about the interval we have here is because the interval in this problem I have looks the following way. Here's the interval they gave me. They didn't give this, but they said negative 3.4 to 3.4. What do you notice is at the very center of this interval, making this the version I got, probably the easiest version I've ever seen of this problem. What is at the very center of that interval? What is at the very center of that interval? At the very center of this interval is what? Just think of how those numbers would average out. 0. So 0 was what they saw as a difference between the means. So hypothetically up here, they would have had to see something like this. That's what they observed in their sample. Now, you don't know exactly how much beef versus meat difference, like what the values of the means were, but you do know that the difference they observed was 0 because that's the center of the interval. Like we don't know it's 10 minus 10, but we do know that mu1 and mu2. Aaron, great to see you here. Happy Cinco de Mayo. Mubot saying hey in the chat. So we do know that the difference is 0. That's something we can confirm. And we also know the what for this interval. We also know the margin of error because we can say plus 3.4 and minus 3.4. Now, our interval is like the easiest one we could get. You should probably find the distance these numbers are apart, which is going to be 6.8, and divide that by 2. 6.8 can be found by doing upper minus lower, and then you would divide that by 2. That's half the length of the interval. So this 6.8 would be the upper number minus the lower number. 3.4 minus 3.4, because it's a negative, so you would actually add it when you subtract it. Confusing, I know, right? So what's the problem getting at? Well, the problem right here says, what do the endpoints of the interval tell us by having opposite signs? So maybe it's the meat hot dogs that have a higher fat content. Maybe it's the beef hot dogs that have a higher fat content, because we don't know. And also, the difference hypothetically could be what for them? Like, hypothetically, the difference could be what? Maybe it's the beef that have a little bit more. Maybe it's the meat that have a little bit more. I don't know. But the difference could also be this, because it goes through this. There could also be what difference? It goes through this, and it's actually the center of the interval. There might be what difference, because this is in our interval. So it's like, well, maybe the difference is just this, because it's in the interval. Maybe the difference is this. Maybe the difference is what? It's quite possible that the difference is equal to 0. It's contained in our interval. That's a believable value. So if you were to do the following, great job, Priya, right there. Yep. Priya, do you reject this null right here, or fail to reject this null? What do you do to this null? Do you reject it or fail to reject it? What would you do here to that null hypothesis? Reject it or fail to reject it? Remember, 0's in the interval. So you're saying maybe the difference is 0. So the null is the difference between the means is equal to 0. Is that believable? If you look up at the interval right there, you'd fail to reject it. Exactly. The interval contains the value you are hypothesizing. So by the hypothesized value being contained in the interval, we could not reject it at a two-tailed test with respective 1 minus confidence level of alpha. In more simple terms, values contained in the interval are not rejected. There's more details, like it's on a two-tailed test with 1 minus confidence level interval of 1 minus confidence level alpha. But the easy way to understand it is, if it's in the interval, you're not rejecting it. We can go more on detail on a question that does that. So the mean fat for the content hot dog is very... Wait. The type of hot dog with the higher mean cannot be determined, because it could be the meat, could be the beef. The negative side indicates beef might be higher by that much. What does the fact that the confidence interval contains 0 mean? Well, we just talked about that. It means the difference in the two samples is insignificant. That means we can't say we really have a difference. If 0 is in the interval, does that mean it's not significant? Exactly. It's not statistically significant. And that's what they're implying right there. And that's what we were talking about, is that you couldn't reject the null hypothesis, which is that there is no difference. So you'd have to believe that. It's believable that there is no difference, so we can't reject that. There is an insignificant difference. The differences are likely by random chance. And best of all, if we were to use this confidence interval to do the two-tailed test, what is the associated alpha level? If we put this on the test, this is nice and fun and easy. What is the associated alpha level for the two-tailed test? Let's draw what this looks like visually. Remember, it's an 89%. So if we were to do the two-tailed test, which is the does not equals alternative, and we did 89%, what is the associated alpha level? And it looks like this. So here is your 89% confidence interval. And then here's the associated alpha level. The curves are meant to be symmetric. Great job here right there. Because all you do is you say this was done at 89%, so the remaining is 11% alpha. As you write alpha as a decimal, they might want it as a percent, but notice how it's just inside outside, because the two-tailed test is the outer, the confidence interval is the inner. So pretty nice and easy, and they do want it as a percent, and that's done by doing 1 minus confidence interval when we were talking about that. Really good question right there. Good practice on knowing what it means that a value is contained in the interval. All that great stuff. We're going to talk about some action items next, and then we got more questions coming up. You could. A lot of times we don't do that. You could, Priya, do that's great. That's worth 100 points right there. Great job, Priya. You could. The test won't mention that, but that is theoretically correct. Good answer right there. That is theoretically correct that you could do that. Test won't do that though, so don't worry about it. In other words, we'll always kind of compare a confidence interval to the two-tailed test, but you could then deduce the alpha level of a one-tailed test that the confidence interval is respectively doing. Inherently, confidence intervals and two-tailed tests are like connected by the inside-outside, but then you could deduce a one-tailed alpha level on it, which would be half of it. So, Priya, that's worth some 500. Really good kind of insight into it to be like, oh wait, couldn't we just figure out the one-tailed? You can, because it'd be half of the alpha of the two-tailed. Yeah. The one-tailed alpha level. Well, we got some action items coming up here. Action items. What's an action item? Here we go. We're here to the main screen. Okay. Let's take a look about some action items and talk about what they are. We got the project noted on this. So when you do action items, this is what usually people lose points on towards the end of their executive summary. You want to be direct. Let's put some things here. Writing good action items. 1, be direct. Tell people exactly what you'll be doing. You have a leadership role here. And it should be clear what we're doing. 2, connect what you're doing to the data results you found. Make sure it references values and why the decision, goes here, Caroline, is being made. So when you think about this, you've really got 2 goals with the action items. You want to make sure it's clear on what you're doing. You want to be like, hey, we're doing this, 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 and the reasons is because the data shows this, 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 so this is why this is the best action. You don't want to come up with an action item that's very kind of like, we'll come up with some right here. I need to use a different data set, so I'm going to pull up some data right here to talk about and kind of talk through and show how we can be direct and we can also connect it to the data. I'm going to use a data set we have. Trying to find a data set we haven't used. Oh, okay. Oh, this is pretty interesting right here. Yeah. Okay. Okay. Whew. Let's come up with some decisions for Brian right here. I think I broke my shiny... No, Shiv. Send me it. You load your old versions. No, version control. Okay, so this is ratings from Brian's class from his students on what they think about Zoom versus in person. So what we're going to do right here is we're going to take and we're only going to compare YouTube. Let's go here to YouTube versus in person, okay? So we got a 2 sample t-test right here. And we're going to go to tables, subset. We're dealing with real data right here, created from Brian's first YouTube versus in-person teaching. Does everyone understand right here? This is data. So what kind of test do you think I'm going to perform to compare ratings of Brian? This is a good tools and techniques question. What test will Brian perform to compare ratings of his first YouTube to his in-class person teaching? What test will Brian perform right here? What test will Brian perform right here? What test will Brian perform? He's going to compare the rating. That's what we're going to be interested in comparing. And I'll show you what we got right here. We're going to go to your fit y by x, compare the rating to the class right here. 2 sample t, Priya, that's right. Because we have 2 means, right? So we have the average rating of YouTube versus the average rating of in-person. And then we're going to compare to see if there's a difference, right? So let's take a look at the data right here. And what do you notice? This is interesting because there's actually more... like the first thing I would notice right here, do you see it also? Might be because there's a larger sample size, but it's very apparent that there's more what in the YouTube ratings. Just looking at it visually right now. We'll compare means here in a second, but visually speaking, there's more what in the YouTube ratings. Visually speaking, there's more what in the YouTube rankings. More math, yep. I think we got that one listed. There's more variation. So there's more like, I love it, I hate it. There's more smaller variations. So what we'd want to use right here is a non-pooled. For those, we don't talk about that in our class, but for a statistician watching this in the future, we use a non-pooled because they look to come from different populations of interest for people. Okay, so let's go here to t-test. And oh, okay. I like it. I like it. The difference observed, see, assuming unequal variance, cool. So using unequal variances, that's good. The right here, the difference we saw between class ratings was 0.05. Now it's in-person minus online. So in-person had higher ratings. Don't do this test I'm about to do. It's the wrong test for you. But you can see the mean of in-person right here was slightly higher. Does that make sense? The in-person class got slightly higher ratings because I'm just doing this output to show you the mean right here. In-person right here had a slightly higher rating. It also comes from a way smaller sample size, so that's why we might not see much of a difference. So the in-person class had a slightly higher rating. And don't do the means ANOVA. We're not doing an ANOVA right here. But here's the thing. The differences we see between the two groups might be what? Oh, thank you, Priya, right there. The differences we see between the two groups, what does this indicate to us right here? Like all these p-values actually indicate this to us. The differences we see between the two groups are probably just due to what? Even though in-person has higher ratings by 0.05 of a point, which is higher, the differences we see in ratings are probably just due to what? Hence high p-value. The differences between the groups are probably just due to what? Hence high p-value. They're probably just due to random chance, random variation. That's what the high p-value indicates. The null hypothesis would be that there is no difference between Brian's in-person teaching and his YouTube teaching in the way students receive it. Does that make sense? The null hypothesis would be there is no difference between, this is the two-sample t-test for the project, so it's also two-sample t for project review. The null is that there is no difference, and maybe we want to see evidence that in-person teaching is better. Does that make sense right here? If we do mu in-person is greater than, and if you're looking at how to read this output, the best thing to do for the two-sample t is to take the symbol right here, for anyone doing their two-sample t, take this symbol and plug it in right here, where you see the minus. Now ignore these because those are just extra things for dash certain things. But we're saying, is there evidence that the in-person teaching has a higher rating? Do you see how this is where the higher would go? So in-person, on average, mu in-person greater than mu online. That is the alternative we are testing right here via the p-value right here, where the null hypothesis would simply be that they're equal, that mu in-person, this is the null. We wrote them in reverse, but that's the null, and that's the alternative we are testing for. Think about what this would mean for Brian. What does this mean? And this is real data, and this is kind of how I make my decisions. What does this mean for the university? What does this mean for Brian? That there really is not an observed difference between how Brian's students receive his in-person. Like we don't, even though there is a mathematical difference, this difference is rather small. We have reason to believe that the ratings Brian's get from his teaching is the same whether it's in-person or online, that there really is no difference. If we see differences, they're probably due to random chance. What does this mean for us? What action items are you thinking of right here as like Brian would be thinking of through this? What action items did Brian choose going forward from this? This was the first time I taught YouTube online. And we saw that there really was no difference between the ratings. Oh, thank you. Well, so when you think about this, if we see there really is no difference, that's kind of a good thing. Because, you know, how I'd write this for my action items here is, you know, the two-sample t-test came back showing that Brian's class has no observable difference between his online and his in-person. So let's see right here. Brian's online class ratings and in-person ratings were found have a statistically significant difference. P-value of 0.2, something like that. Because of this, we recommend that Brian continue teaching YouTube online. His classes are similar to how students receive in-person teaching, and thus our action item is to continue with YouTube. I might even state it plainly for the grader. Awesome, great work there. So this is my action item I created right here from this portion of what we learned. Grammar is not my thing. But does that make sense how an action item is? When you think about the being direct portion of this right here, be as direct as possible. I'm even just saying the action item flat out. Like when you think about the be direct portion, it's more about this. So right there. And then the other portion we mentioned that we need to have is going to be the connect to the report. And so right here, there we go, connect to the report. So if you look at kind of how we write action items, you want to connect what you're doing to the results you found, and then you want to be very direct. And I'm very repetitive, as people know. I repeat myself a lot. But hopefully this makes sense on how to write a good action item, because usually that's where points are lost. People aren't direct enough, like we're going to do this or we recommend this. You know, this is how I make decisions. If I saw the YouTube class had a horrible review and people hated it, I'd be like, well, we're either changing it or we're not doing it. So we use data to make decisions. And yeah, I would quote the values too. Make sure to give the numeric values to back it. Okay, we got a few more. See you in class on Monday, Cerael. Over here to the main screen. Priya, thank you so much. Priya, did you want Store A versus Store B? We've done biking route. Let's go find Store A versus Store B. I think we have time to do, I think, the last two right here. Writing some good action items right there. Okay, yes, please. Thank you so much, Priya. Let's go do Store A for Store B. You know what's going to happen, Priya. What are we going to be doing for this? What are we going to be doing with Store A, Store B? Say it in the chat and I will help out, because we've already got it listed right here. You know what's coming up. It's time for a little
notation, brother.
Okay. Here we go with Store A, Store B. What we're looking at right here is the average amount spent at different stores. People make 80 visits to the first store, Store A, and 70 visits to Store B. Anytime you're doing these problems, make sure you look which one they set up first. There are versions of these problems where you have to be very careful, where it says mu1 is going to be baseball players, and the route problem, which we probably will do next, does reverse B minus A. So look at the way they set it up here with A minus B. This one's set up the way I would do it. The route problem is the one where they don't do A minus B, they do B minus A, causes a little bit of confusion. We have the alpha level, that's the point at which we'll reject the null. We have the degrees of freedom already given to us right here. So we actually don't have to find the degrees of freedom via the calculator. You can if you want, but they give it to you. Okay, so that means we're going over to a new sheet of paper. And we're gonna write it down. So a two sample T is when we have two means, two samples and two means. Mr. T is mean if you're doing drugs. Super nice guy otherwise. Cool. Y bar 1, there's the two means. We're analyzing the difference. That's what that stands for. This is known as the standard error of the difference. We will give these formulas to you on the test right here. It's basically based off S over square root of n, but we're adding together doing the summed standard error of the difference. So that is how we find it right here. It is the standard error of the difference, but it's the sum of the standard errors together. So now that we have this, let's go in here and put in our numbers. I'm going to disappear so I can write a little bit on the screen. We have the two sample means, 43 minus 53. Now make sure you realize this difference will be negative. If you forget your negative, you will get it wrong, even though it's not going to matter so much if we're doing the two-tailed test. On the bottom, we need to make sure we have 20 squared. That's going to be 400 over the sample size of 80. That's going to be 5 when we divide it. Don't need to solve it in my head, but I'm doing it anyways. And 78. So this is going to be close to like 3.4 or so. Let's see if I get close to 3.4. I like guessing at stuff because if I'm guessing at it, I can tell if I get it wrong. I think the whole thing is maybe about 3.4 when we finish this off. There we go. And square root. 3.02. I think Priya's found the test stat right there. Great job, Priya. Super quickly. And Ria, great to see you here too. So now that's the standard error. And then we take that and we do 43 minus 53 and divide by, and there Priya has found it and rounds to negative 3.31. This is the T statistic right here with the degrees of freedom formula. I don't know if we still have it up, but the degrees of freedom formula is the too complicated degrees of freedom. And what do I mean by that? Well, the only thing we need to know about the degrees of freedom formula for the two sample T is that it's too complicated. Degrees of freedom for one sample t is n minus 1. Degrees of freedom for two sample t, we just like to remember it by the memorization technique. It's too complicated. You are not going to use this on the test. You will not solve this on the test. Degrees of freedom one sample, n minus 1. Degrees of freedom two sample, too complicated. Hence why a lot of problems will just give it to you, or we use an applet to solve it. This problem gives it to us, so we don't need to go find it. Okay, so there is the t statistic. I'll go ahead and put that in here. It's probably important we know what kind of test we're doing. So are we doing a greater than, less than, or not equal to test? So we can eliminate this choice because it doesn't have the equals for the null. The options are the greater than, the less than, or the not equal to. You have to look at the researcher's question to see which way the test goes. Okay. By asking, so they say, do customers spend more on a trip to store A or B? So is that going to be greater than? Like, are they spending more at A, which would be this one? Are they spending less at A? You can put the sign right there. Yep, we did that one earlier. Yep. Good question. That was done at the 56-minute mark. 56-minute mark. Check out the 56-minute mark in the video, Ria. Good question. So which sidedness are we doing? The less than, the greater than, or not equal to? Less than, greater than, not equal to. Which one does it sound like we want to do right here? So it doesn't really give a way it goes. Well, we're asking, it does say more, and I think that's the confusing part. But it's saying, you're welcome, Ria, great job. It's not saying do they spend more at A, it's saying do they spend more or at A or B. Does that make sense? I think that's where a lot of people might get this wrong. It says more, but it's like, who makes more money, Jeff Bezos or Elon Musk? Now, I did say more right there, but we're seeing if there's a difference, right? And so this right here will be the not equals. Even though it says more, if I said who makes more money, Jeff Bezos or Elon Musk, I'm not indicating I want to test that like Jeff Bezos makes more than Elon Musk. I want to test to see if there's like a difference right there. Like, who makes more money? I'm not going to indicate it's one. I'm just asking, is there a difference? And that's going to be, and I think that's a point of confusion because the more, but we're just asking, is it store A or store B? We don't really know which way the direction goes on this. So that's a two-sided test. The p-value is going to be very close to 0. It wants 3 decimals. It's probably going to be that. Reason being, we need to go to the t-applet. Yeah, we might have just enough time, Zachary. We'll try. I'll send out the announcement. We're going to try. We'll try to get 2 more in here. Might speed run it. So, yeah, we'll speed run it. And then let's show how we get this p-value right here. To get the p-value, we need to go to the t-applet. Grab your degrees of freedom right here of 155.02. Then enter in, you're doing the two-tailed test, which is already on here, and then your t statistic. And the reason I knew it would be so small right here is because this t statistic is basically off there. Kayla, so good to see you. We did some 320 earlier. Did the reference level stuff. So this is so off the curve, it is basically improbable. And think, since you're so off the curve, remember to enter in your degrees of freedom on the t-applet in the chat. Then enter in your t value here and make sure you're doing the two-sided. It's probably not going to matter so much. That's the one-sided, that's the two-sided. It is double, and it's very hard to see that it's double. You would only see it's double if you were seeing this right here, that the two-sided is double it. Notice how that doubles, but we're so far off the curve that the decimals round down. Maybe. I think Adam Spanbauer's been doing it. I usually do my Kahoots later. I think he did a Kahoot and he did like $80 in prize. I was like, Jeez. I was like, wow. So think about this, the p-value. Humming outside. The p-value. Oh, we should do it today. Oh my gosh. Yeah, we got to do the activity. I can't believe it's Thursday. Last full week. So the p-value is well below the alpha level. So with the p-value well below the alpha level, what are we going to do here? Are we going to reject the null or fail to reject the null? With the p-value well below alpha, so the p-value is well below alpha. What should we do right here? P-value of this, well below alpha. We reject with sufficient evidence. Good pairing of it right there, Priya. Excellent work. We reject with sufficient evidence. So I reject the null. There is sufficient evidence that the means are not equal. Yeah, we've done it. Okay, so let's see. We're going to probably speed run 2 questions right here. I'm going to go back. I'm going to send the announcement to the class for the class coming up. Shiv, I think Spanbauer did it. Let me see. Let me message Spanbauer and say, can you send me a link to your Kahoot? Let me go over here. Let's see. Spanbauer. Let me say, do you have a link? Gave out some good prizes. Was he? You're welcome, Priya. I think he gave out a bunch of Chick-fil-A stuff, and I was like, man, I'll go in there and try to win some. I should put on like a fake goatee or something and go in and watch me lose. Because it's not just if you know it with Kahoot, you got to be quick. So maybe some students, students have been quicker and smarter than I in many ways. So I don't know if I'd win a Kahoot even on a topic I teach. I mean, because especially if I do a stat to 1 Kahoot, I'd probably win those because I don't know. Some people have gotten all the questions right. I had a student or two that I don't know if I could beat at my own Kahoots. I mean, like, you wrote the question, but sometimes you click a wrong button. If I click one wrong answer, all someone's got to do is get a perfect score and maybe beat me. So it'd be pretty interesting, like playing students at my own Kahoot. Student 1, congrats to them. Oh, we got to send that announcement. Oh, yeah, I know. Oh, it's always, yeah, no. Kayla, thank you so much. It is... I wouldn't have it any other way, though. You know, if you're busy, that means people need you. If you're not busy, then everyone's like, we don't need you. Not saying, but sometimes it's good to be not busy. Less stress. There's pros and cons to each. Super busy time was wedding time. That's when, like, it was like I had to be places. And then super busy was week after wedding. Because, make sure right here. Because then class in 20 minutes. See you soon. We'll see. Spanbauer reply. Oh, he hasn't replied yet. Okay, we got it. Okay, we're sending the link out. Sending it to just our section this time for once. Okay, we'll see if Spanbauer replies to that. Okay, let's see. We're going to speedrun 2 questions here real quick. My interval does not contain 0, then that is evidence of a difference. So it'd be evidence of a difference right there. I sent you a few files on Discord, a riddle midterm, a CSV, a script file with my plots, and my Shiny app. Yeah, the one's broken. Oh no, Shiv. I'll probably be taking a look a little later, Shiv. Sorry. Yeah, Shiv, thank you so much. And today's my long day, so I go in and check, and I'm looking at a lot of projects lately. So did anyone here email? And please do. Did anyone here email me your 201 project, and did I look, or Discord me your 201 project? I probably looked over easily over 100 projects in the last, like, it was a lot. It was a lot. I looked over a lot of projects, so, and I give it a quick skim, so I'm sorry if I didn't catch everything on everyone's project. But think about what is the difference in the 2 sample means. Yes, there would be a significant. I did last semester. So yeah, Kale's like, I did last semester. It is significant, Rhea. That is correct, because 0 is not contained in the interval. That is a significant difference, unlikely by random chance. We reject the null hypothesis that 0 is the truth. Brian's looking all crazy right now. Let's see. We got 2 more questions. We're speed running these. Bike route question speed run. And then what was the other one? I think I can do the other one quicker. Someone wanted Cerael, or no, someone wanted, what's the other one? Poor math final question. Was it the, let's see, we'll do the bike route. We'll speed run bike route and drop another one in here real quick if you want. Oh, let's get the poor bike route. Cerael, yeah, Kayla, you are a rock star. I can speedrun Cerael even quicker. Thank you, Zachary. Let's speedrun Cerael even quicker. Kayla, you are a rock star. I truly mean that. Helping out. It's like I know there's one more. All right. Here we go. So Zach, I covered this one more in depth on another video. So I'm going to speedrun this question, show you the quick way of doing it. Caleb remembers the Cerael question. The endpoint of the competition are positive. What does that indicate? That we have evidence that it's completely above 0, that there is a difference between it. Now be careful. If it's completely positive, that means the first mean is higher, because we're doing first mean minus second mean. So there's evidence that the first mean is higher. I got drink some coffee grounds. No more coffee grounds. Let's do this. Okay, so we got the Cerael question. This is a speed run. Please check out one of the earlier office hours this week where I go more in depth on this question. if you're looking at how to solve this and don't want to see a speedrun version. But we're doing this as quick as possible, which means we need that speedrun timer right here. Let's go sub 1 minute. Remember, this is a speedrun. This is not meant to totally explain the problem, but show you how to do it. So here we go. Question start. We're going to right here, we're going to copy the data into jump. We're going to do a copy. Now make sure when you paste the data into jump, you do it with paste with column names. That's edit paste with column names. Next, we're going to go to tables. We're going to go to stack the data. This means we're going to put it on top of itself, so that way we have 2 columns stacked and we have the categorical data right there. We're going to go to analyze fit y by x because we're analyzing a bivariate combination of variables. We're going to put the x variable there, categorical variable, quantitative y variable there. Here we are. We're going to analyze the t-test, which is the 2-sample t-test. This gives us the confidence interval. We now have the answer to the question. So let's go ahead and grab this. I'm going to turn it off screen here so I can type it in a little more quickly. The answers are down here. Okay, so the answer is the lower end of the interval is 31.68, and the upper end of the interval is 39.87. We can see that the adults have less cereal or less sugar in their cereal. The lower end is really off the screen scarily. There we go, and there we go, and that is going to do it. And check the answer, and we've done it. So remember right here, the biggest thing is getting the jump output, and don't shake your screen or that'll happen. But the biggest thing right there is getting the jump output, and yeah. Jump output shows the difference between the 2 means, and we can analyze it right there. So if you want, that is the quick version. Make sure to... wait. I don't know. Just, our friend is here from how are you doing? I hope everything's all right where you're at. Is everything all right with you? I hope you're safe and sound. Our friend from overseas right here. Good to see you here visiting our channel. As always, we always welcome you here. But I hope you're safe and sound and everything's going well where you're at. I wish you the best. And so, Rhea, good questions. If the first mean you're subtracting is beef, then it is. Think of this. Do you see how it's cereal children minus adult? So that's indicate. I think I need a gas for my car, but hey, good to hear you're doing all right. I'm glad to hear that for you. Since this interval starts, or the estimate of the difference is positive, which cereal looks to have more sugar in it? Since the interval is completely positive, which of these cereals looks to have more sugar in it? You can see visually speaking here too, but notice how the difference is positive between what we saw between this cereal and this cereal. So Rhea, this kind of goes to your question. Since this is a positive number, which is at the center of the interval, see 35 is at the center of 31, 39. You can just round them and say 35 plus or minus 4. Since 35 is at the center of the interval, that would be evidence which of the cereals has more sugar. You can also see via the data. So this kind of goes to Rhea's question too, which is more important to analyze the data and understand what it's telling us. I'm 95% confident the true difference between adult cereal and children's cereal. If the first one is beef, yes, because this would indicate which cereal probably has more sugar in it. Because the difference is positive and we're doing children minus adult, since it's positive, the positive number indicates the first mean, which is which. Yeah, if it's positive, then that indicates probably evidence that the first mean is higher. Negative is associated with the second mean, and we have strong evidence here to suggest that children's cereal does have on average more sugar in it than adults via this p-value right here, the greater than, which could be plugged in right there for children's cereal, more sugar than adult. That would be evidence of the first min beef being higher, a significant difference because 0 is not contained in the interval, just like this question here. So this was a good overlap between what you're doing right there, Rhea, and seeing the jump output and understanding how it's found. Does anyone know for 1,000 points how that number 17.6 is being calculated? I do like to throw test-ish questions in here. How is this number right here, 17.6, being calculated? This is a test question. We could blank it out right here. How is that number being calculated? And think of how we do statistics. We take a difference and we standardize it. How is that number being calculated? What mathematics could be done if you didn't have that number with this output now to achieve the number 17? Nice job, Rhea. You got another 100 points right there. What could be achieved? Well, of course. Well, you're doing it. Don't worry. If you don't get 100, that's okay. But congrats right there. And so if you didn't have that number right there, how could you find it mathematically? And we're going to do the other one here real quick. The other one I got to work a lot of math on. The other one I got to be like math. We'll do one more speed run after this. How would we achieve that number? We said it's the difference standardized, right? So the difference standardized It's just that. That's what it is. Let's check it. Take the difference. Standardize it. Remember our number? That's the number. Might have extra decimals on it because maybe they're doing a more exact calculation, but 17.614, and then it diverges a little bit, maybe due to extra decimals we can't see. But that's the difference standardized right there. So confirming that all you have to do is take the difference, divide by the standard error, and that's what's going on the output. The t statistic just tells us kind of the context of the difference. Okay, we got one more question here. It's going to be a speedrun, though, so watch out. You know what this means. Time for a little hacker man right here. Stats 1 hacker man. Let's do this. We got the route question. If you want the longer version of the route question, make sure to check out the previous office hours. I'll state that here at the start of this. Okay. Let's do this. Remember, this is a speed run. If you're watching this in the future, there's a longer version of this on an office hours this week, but we're speed running this question to see how fast we can do it. Woo, get your brains ready. We're gonna have to solve this one. It's gonna take a little bit of work. This one is a know your notation problem. So here we go. Now I get to set it up. Those are the rules of this speed run. Thank you, Easyscape and Cheese, who have made it clear the rules of this speedrun that you can bring it over here to a Word document. There it is right there. Let's speedrun this. Remember, I have a version where I go through this more in depth. So here we go. I'm going to turn off the music. Someone needs some focus on this. Speedrun going. Let's see if we can go sub 1 minute. This is a tough one to go sub 1 minute. Currently, I think, I don't even know who holds the world record. Probably Cheese. He's got the world record on everything. Let's do this. Pen ready. Also in the rules. Let's start it. Okay, we need to find out the difference between B minus A. So we're doing mu B minus mu A, or rather, that's what we're estimating right there. We're estimating it with the sample differences. The long part of this problem is going to be finding the t degrees of freedom that we are going to use, which is the specific t related to the problem. The standard error of this problem, I need to get the speedrun timer out of my way over here. The standard error of the problem can be found by S sub 1. I got this kind of written a little bit weird right here. We're going to do times the square root of S sub 1 squared over N sub 1. I need to disappear. I'm going too slow. Never going sub 1 minute on this one. Plus S sub 2 squared over N sub 2. Now, those are the standard deviations, and those are the sample sizes. Please remember, I do this slower in another problem where I mark everything and show it a much easier way, or slower way. So we need to do the difference between the two routes right here, which is found to be route B was 48 minutes, route A was 45. So 48 minus 45, that's the estimate of the difference, which is an estimate of 3 minutes. The t statistic we'll find here shortly, because that's going to take us using a t-applet. So the standard error for the one route is going to be 5, and the standard error for the other one's going to be 1. Doesn't matter which way you put them in here because both are sampled 15 times. So we go right here, we do the standard errors, and then we can square those, and we get 26 over 15 square root. So that's 26 over 15 square root. Make sure to solve the math. I can't do that one in my head, but I need to find the t with the degrees of freedom now. The t with the degrees of freedom needs to be found via t-applet. So we need to go to the t-applet you're about to see on the screen right here for the t degrees of freedom applet. This is a longer problem to solve. Make sure to watch my example where I do it more slowly. Remember, our sample sizes and our degrees of freedom are going to be found via this method. 15 sample size each, standard deviations of 5 and 1 respectively. Sample sizes are the same, so it doesn't matter which order we put them in. 15.118 is the degrees of freedom, which means we now need to bring this over to a t-applet. I currently have a t-applet on the screen right here, and I think I said 15.11, and that means we need to make a 95% confidence interval using this. So we need to go here to 95% and go between, giving us a t-score of 2.132. Remember that the t is found based on the correct t distribution, which means we need to know the degrees of freedom found previously right here via using the complicated formula that we are not going to solve on the test. So I think I said 2 point. I need to look again at that. 2.132 found via this. Remember, I do a slower version of this. So check out the slower version where I go through each step and talk through it, but this is the speedrun version. And the difference right here is found to be 3. Okay, and that's going to be plus or minus. My handwriting is failing me. And plus or minus, plus or minus, plus or minus, 3 plus or minus this. Ooh, this is not a good version of me solving the problem. Hopefully someone has learned something from this. Okay, so 26 divided by 15 square root times by 2.132. That's the standard error. So 2.81. So 3 plus or minus 2.81. So let's go check out our answer right here. So 0.19, 2.81 is going to be 5.81. The person claims 5 minutes. Yes, that is in the interval. It contains it. Did we get it? Oh my gosh, I was scared. That is a longer, tougher problem, which requires a lot of work on the mathematics. Do remember I do this in another office hours slower. I am teaching in 9 minutes. So we went a little over on office hours, so we did some bonus work right here. Sorry if that one's a little quick. Please remember that was a speed run of the problem. Check out the other office hours where I go more in depth and talk through each step. But hopefully this helps somebody, and it really comes down to this problem, knowing the notation and identifying each part of the notation. So make sure you have the notation, and if you solve each bit of the notation and plug it in, you can get it. So it comes down to knowing the notation. With that, we'll be back here later today. We could do this slower later today if you like, but swing by later today, and I'll see you then. Bye for now, everyone. Bye.